Good day, grade 12 chemistry students. Today we're continuing to learn about equilibrium. We're going to focus on both the qualitative and quantitative aspects of the chemical systems that are at equilibrium. We're going to focus on solving problems. Today you are going to learn about Q. Q will allow us to predict which way an equilibrium will shift when it is disturbed or stressed. So here we have an equilibrium. A plus 2b equilibrium arrows equals 2c plus d. Now, what is K? K is an equilibrium constant. That's what this EQ means. And what it really is just product concentration, so some equilibrium concentrations of C, times the equilibrium concentrations of D. These are both products. And we divide it by the concentrations of the reactants, which are A and B, when everybody is at equilibrium. So there's a whole bunch of different values that we can plug in for these, but what will happen is we'll always get the same value of K. So what does K tell us if it is a very large value? Well, one thing we have to do here first is I'm not going to actually have to put in the coefficients, because the coefficients actually become exponents. So this B will have a little squared here, and this C will also have a little squared here. But that doesn't really matter as far as when we talk about K being very large. If K is very large, that means you have a lot of products and very, very little reactants. And I'm just thinking about if I put big numbers on the top of this equation, I'm going to get a very, very large number. Okay, and so that means that when K is very large, we have lots of C and D. So what if K is very small? Well, it's obviously just the opposite. It's going to mean that, again, if K is very small, that means we're going to have lots of reactants at equilibrium, where if it's very large, we have lots of products. So what happens to the K value when we change the temperature? Well, when you change the temperature, you get a new equilibrium, okay? And that also means that the K value will change as well. Now, depending on the enthalpy change, if we change the if it's endothermic or exothermic, if we change the temperature, that is going to impact K. We'll talk about this a bit more in class, but just remember that when you change temperature, K changes. Also remember, if you change pressure, you are also going to change the K value as well. But also remember that pressure only impacts gases. It doesn't impact liquids or solids. Because liquid concentrations are incompressible, they don't come into play at all. We're going to learn that later that solids don't make it into our equilibrium expression at all because they are completely solid and they don't really have a concentration. We'll talk more about this as well. So let's get through to the problem at hand. We're going to learn about Q. Okay, so this tells us that at this particular equilibrium, 2HI equals H2 plus I2, I can see that it's balanced. It gives you a specific temperature. It tells you that K is equal to 0.02 when it's at this 445 degrees Celsius. Because K is less than 1, I know that it's more reactant concentrations at equilibrium, okay? If K was larger than 1, I would know it's more than products. I would know it's more products at equilibrium. So here we have some equilibrium values for H2 and I2, and we want to know if they're at equilibrium. So we have two scenarios. So if I plug these, if I make a K expression from here, and I'll do that, and I plug these values in, if the K value is equal to 0.02, then I know it's at equilibrium. If it's bigger, if I plug these values into a K expression and I calculate K, and it's bigger than this value here, then I know that it is actually more products than what it should be at equilibrium. So therefore, it's going to shift towards the reactants. So we'll talk about what that looks like right now. So let's show you exactly what I mean. So here what we're going to do is I've boiled out the numbers for you. I've pulled out all the numbers from the question, and we have A and B. So we want to see if these concentrations here in A are at equilibrium. So we need a K expression. So it's going to be products over reactants. So no, if you're going to put any numbers into this K expression, they have to be at equilibrium. Now these numbers down here, we don't know that if they're at equilibrium or not. They might be. If I plug them in there and they're equal to 0.02, we know it's at equilibrium, but we're not quite sure. So we call this the trial ion product, and it's actually known as Q, okay? So Q is just a trial. Actually, it's not the trial ion product, it's just the trial. It's not a trial ion product, just a trial. So let's plug our numbers in. Now we call it Q because it's a trial and because we're not certain if these numbers are going to equal to 0.02. So let's plug those values in and let's do a little bit of math. So Q is going to be equal to this. Let's plug our numbers in. So you can see here that I've just plugged my values in for H2, which is right here, it's 0.04, and I2, which is 0.01 I plugged in, and 0.14 squared, which is HI. And you can see that I get a value that is 0.02. So what does this mean? This tells us that for A, these concentrations in A are at equilibrium, okay? And they're at equilibrium because when we plug in our values, we can see that it equals 0.02. Now 0.02 means that it's at equilibrium, so indeed this is exactly like K. Let's do the same thing for B. So we're going to just plug in our values and do a simple calculation. So what I did for the second one is I plugged in my values for B, and this is we don't know if these values are at equilibrium or not. And we just plug them into our expression, which is exactly like K, except we're calling it Q because it's a trial. We're not sure if it's going to give us an equilibrium value, and it doesn't. It gives us 0.3375. Now this number is larger than 0.02. So K is 0.02. Our Q value is greater than K. That means it's going to shift towards reactants. I know this because this number is too big. And that means to make this number smaller, it means I need more on the bottom of the equation. Now recall that this is where the reactants are. So if I want to make this value smaller, this has to shift towards reactants. So you don't have to understand that exactly, but if you know that Q is larger than K, it's going to shift to the reactants. We understand that if we have a larger value, we're shifting towards the reactants to make this value smaller. So in summary, you can write this down. You can pause the video and write this down if you'd like. But the reaction quotient is an expression that is identical to the equilibrium constant expression Kc or KEQ. Kc stands for constant. You could just say EQ there. But its values that are going into the equations are not necessarily at equilibrium. So quotient is our Q. It's a trial in summary. Again, to summarize, if Q is equal to K, we plug some values into that expression, and it's equal to K, then it's at equilibrium, just like the example A. If it's larger than K, we're going to say that's shifting towards reactants because the products to reactant ratio is too high. If Q is less than K, then obviously it's going to shift towards products. So, in summary, when do we use Q? We use Q when we have some concentrations and we don't know if they're at equilibrium. We have a K value, we're not sure if it's at equilibrium, so we just plug our values into the Q expression, which is exactly the same as the K expression, and we compare the K value to our calculated Q value. We then look at these scenarios and tell if it's going to shift or if it's already at equilibrium. That's all for today. We'll do some questions tomorrow. Have a great evening.
Who sleeps in best when you've got the sunrise? Wasting time watching infomercials live on Channel 9. Us and Billy Mays, no